Hi, my name is Preston Provins, and I'm an engineer on the Metal Framework team at Apple. And I'll be joined later by my colleague, Scott. I'll share the additions coming to Metal that combine machine learning and games. And Scott will introduce the GPU tools additions designed to enhance your debugging experience for machine learning in Metal 4. I'm excited to share how to combine Metal 4 machine learning and graphics in this session. If you're interested in what all Metal 4 has to offer, check out the Metal 4 Foundations talk to learn about what else is new to Metal 4. Machine learning is transforming games and graphics with techniques like upscaling, asset compression, animation blending, and neural shading. These techniques push the frontier of creativity and immersion. They simulate complex phenomena, enhance visual fidelity, and streamline the exploration of new styles and effects. Core ML is fantastic for a wide range of machine learning tasks, such as segmentation, classification, generative AI, and more. It makes it easy to author machine learning models. If your application of machine learning requires tight integration with the GPU timeline, Metal 4 has you covered. In a typical frame, a game may perform vertex skinning in a compute pass, rasterize the scene in a render pass, and apply anti-aliasing in another compute pass. Anti-aliasing is typically done using image processing techniques, such as temporal anti-aliasing. Cutting-edge techniques replace these traditional methods with the machine learning network. This network upscales the image, allowing the rest of the rendering to happen at lower resolution, improving performance. It's also becoming more common to execute tiny neural networks inside a shader. For example, a traditional fragment shader would sample material textures, but groundbreaking techniques use small neural networks to decompress textures on the fly and achieve higher compression ratios. This neural rendering technique compresses material sets to 50% of the block compressed footprint. In this session, we'll meet tensors, Metal 4's new resource for machine learning workflows. We'll dive into the new machine learning encoder, which runs entire networks on the GPU timeline, alongside your other draws and dispatches. We'll introduce Shader ML, which lets you embed machine learning operations inside your own shaders. Finally, we'll show how you can seamlessly integrate ML into your application with the Metal debugger. You're already familiar with buffers and textures. This year, Metal 4 introduces Tensor, a new resource that lets you apply machine learning to data with unprecedented ease. The tensor is a fundamental machine learning data type that can be used for compute, graphics, and machine learning contexts. Machine learning workloads will extensively utilize tensors. ML Encoder uses tensors to represent inputs and outputs, and Shader ML uses tensors to represent weights as well as inputs and outputs. Tensors are multidimensional containers for data and are described by a rank and number of dimensions for each rank. Tensors can extend well beyond 2 dimensions, providing the flexibility to describe any data layout you need for practical machine learning usage. Textures, for example, are limited to 4 channels at most and have strict limits for the extents that depend on the texture format. For machine learning, it's common to use data that has more than 2 dimensions, such as convolution operations. Using a flat representation of data, like MTL buffer, would require complicated indexing schemes for data with multiple dimensions. Indexing multidimensional data in a tensor is way simpler because the stride and dimension of each rank are baked into the tensor object and automatically used in the indexing calculations. Let's work through the process of creating a tensor. The tensor's rank describes how many axes it has. This tensor has a rank of 2. It contains rows of columns of data. The extents of the dimensions describe how many data points are along that axis. The data type property defines what format of data the tensor is wrapping. Usage properties indicate how the tensor will be utilized. Machine learning for ML encoder, compute or render for usage inside of your shader programs. It's also possible to combine usages, like the usage property for textures. These are the important tensor properties that should be populated on a tensor descriptor object. Now, let's make a tensor in code. With the descriptor properties filled, Create a new tensor by calling new tensor on a device object. Tensors are created from either a device or buffer object. However, tensors created from device offer the best performance. Similar to how textures can be swizzled, creating a tensor from device object results in an opaque layout that is optimized for reading and writing. Now, let's focus on creating tensors from a pre-existing buffer. Unlike tensors created from a device, tensors from buffer aren't assumed to be tightly packed, so you need to specify its strides. The innermost stride should always be 1. The second stride indicates how many elements are jumped over when the row index is incremented. It's possible the source buffer contains padding, such as unused columns at the end of the row. Padding needs to be accounted for so the tensor wraps the appropriate elements. To create a tensor from an underlying buffer, set the data type and usage properties like you would for a device-allocated tensor. Then, fill out the strides property of the tensor descriptor, so the resulting tensor will appropriately wrap the contents of the buffer. Finally, use the new tensor method on the source buffer. Now that we know how to allocate and create tensors, let's dive into the new machine learning encoder to add ML work to the GPU timeline. Metal 4 enables compute and render commands to be easily added to the GPU timeline, with the Metal 4 compute command encoder and Metal 4 render command encoder, respectively. This year, we're taking unification even further by adding machine learning work to the GPU timeline. The Metal 4 machine learning command encoder enables full models to run alongside and synchronize with other Metal commands on the GPU and ensures seamless integration with other Metal commands. It's a new encoder for encoding machine learning commands. It has an interface similar to the compute and render encoders. The Metal 4 synchronization primitives also operate with machine learning commands, just like with compute and render. Synchronization enables control over work orchestration and facilitates parallelization to maintain high performance. The ML encoder creation workflow can be separated into 2 parts, offline and runtime. The offline portion of the workflow takes place prior to application launch, and the runtime portion will happen during the application lifetime, such as in the middle of a frame. Let's start with the offline portion of the workflow, creating a metal package. A metal package is a container for one or more functions that each represent an ML network that you can use in Metal to execute machine learning work. This format is optimized for loading and execution with Metal. To create a Metal package, you first need to have a Core ML package. Here, we use Core ML Converter to convert from the ML framework the network was authored in, such as PyTorch or TensorFlow, into a Core ML package. Here's an example of exporting a PyTorch model using the Core ML tools library in Python. Simply import the tools and run convert on the model to generate an export. Finally, save that export as an ML package. There's one thing I'd like to highlight here. Not every Core ML package is an ML program, and only ML programs are supported. If the Core ML package was exported on an older OS, check out this article to learn more on exporting those Core ML model files as an ML package. With the Core ML package created, it is as simple as running the Metal Package Builder command line on the saved model to produce a Metal package. This converts the Core ML package into a format that can be efficiently loaded at runtime. So that's it for creating a Metal package. The offline portion of the workflow is complete, and the rest is carried out at runtime. To compile the network, first open the Metal package as an MTL library. Create a function descriptor using the name of the function that represents the network in the package, in this case, the main function. To compile the network, create a machine learning pipeline state. This is done using a machine learning pipeline state descriptor with the function descriptor. If the network has dynamic inputs, specify the size of each input on the pipeline descriptor. Compile the network for the specific device by creating the machine learning pipeline state with the descriptor. That's how an ML pipeline state object is created. Now the next step is creating the machine learning command encoder and encoding work. Let's take a deeper look at using the ML encoder object to dispatch work on the GPU timeline. Simply create the encoder object, just like creating an encoder for compute or render. Set the created ML pipeline state object and bind the inputs and outputs being used. Finally, dispatch the work using the dispatch network with intermediates heap method. The machine learning encoder uses the heap to store intermediate data between operations. Instead of creating and releasing buffers, it enables the reuse of resources for different dispatches. To create this heap, create a heap descriptor and set the type property to heap type placement. You can get the minimum heap size for the network from querying the intermediates heap size of the pipeline. Set the size property of the heap to be greater than or equal to that. After encoding your network dispatches, end encoding and submit your commands to run them on the GPU timeline. As previously mentioned, Metal 4 synchronization primitives also operate with machine learning commands, just like with compute and render. Work that doesn't depend on machine learning output can happen in tandem if synchronized correctly. Only the work consuming the network output needs to wait for the scheduled machine learning work to conclude. To synchronize ML encoder dispatches, you can use standard Metal 4 synchronization primitives such as barriers and fences. The new machine learning stage is used to identify ML workloads and barriers. For example, to make your rendering work wait on outputs produced by a network, you could use a barrier between an appropriate render stage and the machine learning stage. Let's look at ML encoder in action. In this example, ML encoder is used to dispatch a fully convolutional network to predict occlusion values per pixel. Evaluating this requires careful synchronization. The depth buffer and view space normals are populated prior to launching the ML workload. While the network is processing the data, the renderer dispatches other render-related tasks in parallel and waits for the neural results before compositing the final frame. ML encoder isn't just limited to processing full frame information for games. You can use it for any network that fits into a real-time budget and leverage Metal 4 synchronization primitives to however best suits your integration needs. That's how Metal 4's machine learning encoder makes it easy to run large machine learning workloads on the GPU timeline. To summarize, machine learning is joining compute and render in Metal 4 through the ML encoder. ML encoder enables entire networks to run on the GPU timeline. Resources are shareable with other GPU commands, and the robust set of Metal 4 synchronization primitives enable high-performance machine learning capabilities. Metal 4 also introduces Shader ML for embedding smaller machine learning operations inside your existing kernels and shaders. Cutting-edge games are adopting machine learning to replace traditional rendering algorithms. ML-based techniques can offer solutions for global illumination, material shading, geometry compression, material compression, and more. These techniques can often improve performance or decrease memory footprint. As a motivating example, let's consider neural material compression, a technique that enables up to 50% compression when compared to block compressed formats. With traditional materials, you sample material textures, such as albedo and normal maps. Then you use the sampled values to perform shading. With neural material compression, you'll sample latent texture data, perform inference using the sampled values, and use the network's output to perform shading. Splitting each step into its own pipeline is inefficient, since each step needs to sync tensors to device memory, operate, and sync outputs back for later operations. To get the best performance, your app should combine these steps into a single shader dispatch. With Shader ML, Metal enables you to run your ML network directly within your fragment shader, without having to go through device memory between steps. You can initialize input tensors, run your network, and shade only the necessary pixels each frame. That improves your runtime memory footprint and your game's disk space. Let's take a look at neural material evaluation in greater detail. Initializing input tensors can be split into two parts: loading the network weights and building the input feature tensor. The input feature tensor is made by sampling bound textures with a UV coordinate for the fragment. Inference is where the input feature tensor is transformed by learned weight matrices to extract features, compute activations, and propagate information through layers. This evaluation is repeated for multiple layers, and the result is a decompressed material. Finally, the decompressed materials are used for the shading calculations of the fragment. Let's see how to initialize our input tensors with shader ML. First, let's declare a fragment shader that will utilize shader ML and pass in network weights. Start by including the new metal tensor header. We use the tensor type to access the network weights. Tensors are bound to the shader using buffer binding slots. It's also possible to pass in tensors using argument buffers as well. The tensor type is templated. The first template argument is the tensor's data type. These tensors were created in device memory, so we use the device address space qualifier. The second argument represents the tensor's dimensions and the type to be used for indexing into the tensor. Here we're using dextents to define a rank 2 tensor with dynamic extents. With that, our fragment shader is set up. Let's implement the neural material compression algorithm. With the weights of the network passed in, we can create the input tensor by sampling 4 latent textures. Tensors are not just a resource that can be bound, you can also create inline tensors directly within your shaders. Create a tensor wrapping the sampled values and use it for the evaluation of the network. Inline tensors are assumed to be tightly packed, so there is no need to pass strides at creation. With that, initializing the input tensors is complete, and we're all set up to infer values from the neural network. Evaluation transforms inputs using learned parameters, which are then activated. The activations are passed to subsequent layers. The final layer's activations form the decompressed material. This year, Metal introduces Metal performance primitives to make tensor operations accessible in the shading language. This library is a set of high-performance APIs that enable performance-portable solutions on tensors. It provides matrix multiplication and convolution operations. Matrix multiplication is at the heart of neural network evaluation. We'll use the MapMul 2D implementation provided by Metal performance primitives to implement a performance-portable network evaluation routine. To get started, include the new Metal performance primitives header inside your Metal shader. The parameters of your matrix multiplication are configured using the MapMul 2D descriptor object. The first set of template parameters specify the problem size of the matrix multiplication. The next set of template parameters control whether the inputs to the matrix multiplication need to be transposed when performing the operation. And the last template parameter controls your precision requirements. In addition to the descriptor, the MapMul 2D operation must be specialized with the number of threads that will be participating in the operation. Here, since we're within a fragment shader, we'll use execution thread to indicate that the full matrix multiplication will be performed by this thread. Then, run the matrix multiplication with that configuration. Finally, activate each element of the result of our matrix multiplication using the ReLU activation function. This process is repeated for the second layer to fully evaluate our network right in the shader. After evaluation is complete, the decompressed materials are available to be used for shading. The output tensor holds channel information, which can then be used like any other value sampled from a texture. Here's a real-time demo of neural material compression compared to traditional materials. There's no perceived quality loss from using neural materials, especially when shaded. Here's the base color in isolation. It's still very difficult to notice any differences between neural materials and traditional ones. And yet, neural materials use half the memory and take up half the disk space. Tensor operations aren't exclusive to just fragment shaders. They can be used inside of all functions and all shader stages. If an entire SIMD group or thread group will be doing the same operations on the same data, you can leverage the hardware to your advantage by choosing a larger execution group. But if your tensor operations are divergent with respect to data or exhibit non-uniform control flow at the tensor operation call site, you must use a single thread execution group. Other execution schemes assume there is no divergence and uniform control flow for the execution group. To summarize, you can now perform ML operations like matrix multiplication and convolution in your own shaders. Shader ML makes it easy to perform multiple ML operations in a single shader. This is cache-friendly, requires less dispatches, and uses less memory bandwidth, especially when using smaller networks. And Shader ML gives you the fine-grained control you need to create custom operations. It's never been easier to implement cutting-edge ML techniques in your metal apps. And that's how you can use Shader ML to embed neural networks into your shader program. Now, I'll turn things over to my colleague Scott to show how Metal 4's new debug tools make debugging machine learning workloads a breeze.
Hi everyone, I'm Scott Moyers, and I'm a software engineer on the GPU Tools team. Earlier, Preston showed you an application that uses machine learning to calculate ambient occlusion. The app encodes a machine learning network directly into its metal rendering pipeline. While helping develop this app, I hit an issue where the output had some severe artifacts. Let me enable just the ambient occlusion pass to highlight the problem I had. There should be shadows in the corners of objects, but instead there's lots of noise and the structure of the scene is barely visible. I'll show you how I use the new tools to find and fix this issue. First, let's capture a GPU trace of this app in Xcode. To do that, I'll click on the metal icon at the bottom of the screen, then the capture button. Once the capture completes, I can find my captured frame available in the summary. The debug navigator on the left provides the list of commands that the application used to construct the frame. For instance, the off-screen command buffer contains many encoders, including the gbuffer pass. And the next command buffer contains my machine learning encoder. Using Metal 4 allowed me to have fine-grained control over synchronization. And whilst I was careful about setting up barriers and events between dependent passes, I wondered if a synchronization problem could be causing these issues. To check this, I turned to the dependency viewer, which is a useful tool to get an overview of the structure of your metal application. I'll click on the dependencies icon at the top left. With this interface, I can see all of the application's commands along with any synchronization primitives such as barriers and events. Zooming into a command encoder reveals even more detail. There's the completion of my first command buffer. The command below it copies the normals into a tensor. Then there's a barrier, followed by a machine learning encoder. I'll zoom back out so I can review the overall structure. My new ambient occlusion pass is in the command buffer on the right. Before I added this pass, the application was working fine, so I can assume the dependencies within the top and the bottom command buffer are correct. I'll inspect the new command buffer containing the machine learning encoder. Before the command buffer can start, there's a wait for a shared event signal. Then at the bottom of the command buffer, there's a signal to unblock the next one. So there can't be any other commands running in parallel with this command buffer. And within the command buffer, there's barriers between each encoder, ensuring that each command executes one after the other. I was fairly confident at this stage that there weren't any synchronization issues, at least within this frame. With that ruled out, I decided to check the ML encoder directly. Clicking on the dispatch call for the ambient occlusion network takes me to its bound resources. On the right, the assistant editor is displaying the output tensor. I can see it has the same artifacts as the running application, so clearly it's not correct. I'll double-click the input tensor to display it next to the output. The input has what I would expect for view-space normals. The objects facing a different direction do have different component intensities, so the problem must be inside my machine learning network. Let's go back to our bound resources view. And this time, I'll double-click Network to open it in the ML Network Debugger. This tool is essential for understanding what's happening inside the model. This graph represents the structure of my ambient occlusion network. I wrote it in PyTorch, and in my targets build phases, I do what Preston suggested earlier. I export it as a core ML package, then convert it to an MTL package. The boxes are operations, and the connections show data flow through the model from left to right. I wanted to find out which operation was responsible for introducing the artifacts. I knew the final output was bad, and that the input was good, so I decided to bisect the graph to narrow it down. Let's pick an operation roughly in the middle. Selecting an operation shows its description on the right, along with its attributes, inputs, and outputs. What's more is that I'm able to inspect the intermediate tensor data that any operation outputs. I'll click on the preview to open it in the tensor viewer. I can see the artifacts are already present here, so I'll check an earlier operation. This operation also has artifacts in the output. Let's inspect its input. This tensor, however, appears to be highlighting edges in the scene, which is expected. The input to our network is the edges extracted from our depth buffer, so something must be going wrong within this region of the network. This stitched region can be expanded by clicking on the arrows in the top left of the operation. From the order and the types of these operations, I recognize this as my signed smooth step function. It first takes the absolute value of the input, then clamps the value between 0 and 1. But then it's raising the result to the power of itself, which doesn't seem right to me. I don't remember there being a power operation in the smooth step function. Let's jump into the Python code to find out what's going on. I'll stop the debug session and go back to the source code. The model I'm running is in this class called LightUnet. I'll navigate to its forward propagation function to check it's doing what I expect. The first custom operation it's performing is signed smooth step, which is the stitched region I saw in the ML network debugger. I'll jump to its forward propagation function. This should be a straightforward smooth step operation where I maintain the sign of the input. But on this line, I can see the bug. I typed too many asterisks, making my multiply a power operator. Let's delete that extra one and try running it again. And there you have it, a working implementation of neural ambient occlusion using Metal 4's built-in ML command encoder. In this demo, I showed you how I use the Metal debugger to debug a Metal 4 machine learning application. First, the dependency viewer helped me validate synchronization. After that, I inspected the inputs and outputs of the network using the tensor viewer. This verified the problem was inside the network. Finally, I used the ML network debugger to step through the operations in the network and pinpoint the issue. These tools are part of a larger family of tools available for debugging and optimizing Metal apps. Now, let's recap what we covered today. Metal 4 introduces MTL Tensor, a new multidimensional resource designed specifically for machine learning data. Tensors provide flexibility for complex data layouts beyond 2 dimensions, and with baked-in stride and dimension information, greatly simplifies indexing. New features in Metal 4 make it possible to combine machine learning workloads into your Metal pipelines. The ML command encoder enables entire machine learning networks to run directly on the GPU timeline. This allows seamless integration and synchronization with your compute and render work. For smaller networks, Shader ML and the Metal Performance Primitives library allows you to embed machine learning operations directly into your shaders. Lastly, the Metal debugger gives you incredible visibility into what's happening in your Metal 4 application. The new ML network debugger makes it easy to understand your network and how it executes on device. This kind of insight is essential for ensuring correctness and optimizing performance. For some next steps, try out Metal 4's ML encoder and Shader ML for yourself by installing the latest OS and Xcode. To find out more about how the Metal developer tools can help you, head over to the Apple developer website. And to get the most out of your Metal 4 application, make sure you check out other Metal 4 talks. We're truly excited to see what you will build with these new capabilities. Thank you.